Hello everyone and welcome to another Würth Elektronik ISIS webinar. My name is Eleni Stark and I will moderate this webinar today. We are very pleased that you took the time to participate in our today's webinar. The topic of the webinar will be small, inconspicuous, underestimated. EMC ferrites are more than just bird seeds on the PCB. Our speaker today is our product manager, Joanne Wu. She will hold today's webinar and also answer your questions. Before we start the webinar itself, I would like to point out one thing. You'll be muted during this webinar today. This means that you cannot ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us all your questions during the webinar at any time via the chat function. And you'll find the chat function in the webinar control panel. The webinar will be about 30 minutes long. The chat questions will then be answered in a question-answer session following the webinar. There are 10 to 15 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email after the webinar. And if you still have any other questions left after the webinar, just email us at isis-webinar@we-online.com. We will try to answer all questions promptly. At the end of the webinar, you'll be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our webinars. The link to the recording of today's webinar, as well as the presentation, will be sent to you in a separate email several days after the webinar. And you can also watch the recording of today's webinar a few days later on our website under the navigation point webinars, or also on our Würth Elektronik YouTube channel. We are also just right here for you now via our chat function. And like I said before, if you have any questions, just email us at our general ISIS webinar email address, or also directly to the product managers for this webinar today on the mentioned email address. Now I will hand over to our speaker, Joanne Wu, and I wish you an exciting webinar.
Hello and good afternoon. My name is Joanne Wu, and I'm a product manager for EMC PCB ferrites. Our topic today is small, inconspicuous, underestimated. EMC ferrites are more than just bird seeds on the PCB. As you can see in this photo, it seems that ferrite beads are quite big. However, there's a trick, and we've used a mini dies, so technically the PCBs aren't as big as you think. In today's overview, I'll do a quick basic introduction, then I'll move on to high frequency ferrite beads, then an overview of the production process, to further on the influence like DC bias and temperature affect the ferrite bead in application, and lastly to conclude a pulse current definition for inrush currents. As we all know, there are two different types of EMI problems. Ones that are received, conducted through, for example, power supplies, cables, and another one that is radiated out of our application device. In general, SMD ferrites are suited for radiated emissions. As we can see here, this is a radiated emissions test, and there are different limits that we need to comply. This one here is shown for an industry standard. The emissions here are over the standard, and there are different ways to solve EMI problems. One way is to use a ferrite bead to smooth out the noises. And here is one where we've used a ferrite bead, which then they pass the test. So, on to the basics. Ferrite material. What is a ferrite material? Ferrite is part of the ceramic family. It's an inorganic material and multicrystalline. This means that a ferrite is quite hard in structure. However, if you drop your PCB or if you drop a ferrite ring core in general, you can see that they break easily. That's because they are brittle. Ferrite material is based out of nickel zinc or manganese zinc, however, mostly nickel zinc. And it has the ferrite component or ferrite iron oxide component, which everybody knows more or less as rust. The characteristics of a ferrite: it is just a passive device. It's like an inductor. However, instead of storing the energy, here you want to remove this energy in the form of heat. The electrical properties depend on which frequency range you are working in, and the material and which material, which I've mentioned before, nickel zinc or manganese zinc. One main electrical property that we see for ferrites is the impedance. We know that they are categorized, is made up of the real part here and the inductive part, positive or negative. This is a typical impedance curve from one of our data sheets. We show 3 curves: the impedance, the reactance, and the resistive part. In the first part, in the low frequency region, the bead acts more inductive. In the green area, it reacts more resistive. So this is where the self-resonant frequency is. And when it comes down, the ferrite bead reacts more capacitive. As the main function of the ferrite bead is to dissipate the noise, we would treat it more like a resistor and use it within this region up here. Following is the construction or the structure of the ferrite bead. It has a main ferrite body core with silver layers, printed layers. Mainly there are 2 types. One here, which is a vertical winding from terminal to terminal, and the other is a horizontal winding. So starts from one side and coils up and ends on the other side. This here we called as a standard structure, and this on the left we categorize as a high frequency structure. So here's a 3D model to better show the layers, the inner layers. But how does the structure relate? How does the structure relate to the classification of high frequency and standard? As we can see in this diagram here, the capacitors or the parasitic capacitance is within the internal layers from one terminal to the other. This here we call is summed up in series. In the standard one, the parasitic capacitance are from terminal to inner layer back to terminal, and so on. And here when we sum it up, they are in parallel. As we can see from this vector diagram, when you have less capacitance, you have a smaller decrease in the imaginary field. And with more capacitance, obviously lower. So when we take the magnitude of the impedance, your Z would be higher when you have smaller capacitors. This can be seen in the impedance curve, where typically, if you take the tip of the SRF point, they are shifted nearly by a decade. We have an application note coming soon that will feature the differences between high frequency and standard. So an insight into the production process. Firstly, we have ferrite powder and binding material. This is mixed together. Then we go through a ball milling, which makes the particle or grain size smaller. Then we tape cast, we fill out the ferrite paste, and it goes through a printing process. After the printing process, it goes into lamination. Lamination's where you compress all the layers together. Afterwards is a cutting process where you dice up each panel into your chip beads. After cutting is a burnout. This phase is where we try to burn out all the binding material that was added at the start because it's not part of the ferrite. It's not needed. This is also another reason why the chip bead ferrites don't have a UL certification. It's not required since all the flammable material has already been taken out of the component. After the burnout phase is sintering, where it goes through the oven. Then each part is then tumbled. Tumbling is to smooth out the edges. Termination happens to dip both sides of the chip bead to make a connection. Then it goes through the oven again. Then plating, where you put on layers for your soldering. And that is the completion of a ferrite, a multi-layer ferrite. Then it goes through sorting, which you look at the electrical specs to make sure they're qualified, and appearance, how does it look? And lastly, they all go into a reel. So I've highlighted here 4 boxes, which we will have a look into the process. Mesh printing. First, you would calibrate all your devices, so to make sure that all the meshes match up in line with the panels. This is a mesh board where you can see little white cutouts. So this stencil would be where all the silver layers be printed on. In the last clip here is the ferrite printing. This is when the ferrite paste is put on and rotated to get each winding, to get your coil windings. Yeah. The electroplating of nickel and tin is the dipping after you've done your termination. You have your ferrite core, then we add on a silver layer, or sometimes mixed with glass. Then there's a nickel layer. Nickel layer is good for making sure that you have no tin whiskers. And lastly, you have a matte layer, and that finishes your termination. Here they go into different barrels of different pools of chemicals for each of these layers. Electrical sorting happens in a big ring where each components are sorted out and they are tested here. So there are little slots which each part is measured to make sure that they fit into specification, and afterwards are sorted into different categories. It is then gone through an AOI, which is automatic optical inspection. Here we use different colors, different LEDs to make sure the visual looks, the physical looks of a PCB. Of a PCB ferrite. And anything that looks different strange is automatically taken out. Onto a measurement topic is the rated current. So this is a typical setup of an impedance to measure the impedance using an impedance analyzer. Here there are two fixtures. This fixture here can go up to 3 gigahertz plus a DC bias adapter to put in your DC bias current. However, as you can see that this DC bias adapter is limited up to 5 amps, all our datasheet information we can only show up to 5 amps. This is the same situation with the impedance, so everything is up to 3. Hence, now we have made a new measurement setup where we can measure up to 20 amps DC bias is possible and up to 8 gigahertz. At the same time, we try and reproduce the reality of a chip being used on a PCB. Here is an example where we measure up to 8 gigahertz and the capability of this part up to 10 amps. For the temperature, different materials have different Curie temperatures. In this case, you can see that when you go above the Curie temperature of a chip bead ferrite, it will then go into a saturation mode. This is where the permeability of the ferrite is close to 1, which is close to air. That means the ferrite will no longer work as a ferrite. For the temperature, we do measurements from minus 55 degrees to 160 degrees. In our data sheet, we specify it at room temperature. Here is an example of 3 different materials. The first material has a Curie temperature less than 130 degrees. This is where you can see that at 160 degrees, it's saturated so much that it no longer looks like the original impedance curve. At Curie temperatures of greater than 130, so roughly around 180 or so, the saturation is much better. It's closer to its original. And with Curie temperatures much further away at more than 180, which is usually at 220 degrees, it's just a drop at your resonance frequency. A last topic is about inrush currents. So for the inrush current, usually when your capacitor charges up very fast and discharges, you get a possibility of high peak currents. This is when you think, okay, is ferrite able to handle it? It is easy to destroy a part, as you can see in this photo where they crack usually within the silver layers, or they shatter here, or at the end terminals. However, there are different types of ways you can withstand. You can add a capacitor at the start to avoid peak currents to destroy your part, or you can design in an SMD ferrite. However, it can only go up to the maximum rated current. If you have situations where you're using large main powers up to 100 amps, then it's best to substitute with wired ferrites. We have one particular series called the MPSB, where we have a new definition, not just the usual rated current. There is a specific MPSB specification that we make sure it can handle these inrush currents. From this chart, we test a pulse length of 8 milliseconds at 100 amps. And as you can see, depending on part, let's just take, for example, this black one. At 8 milliseconds, it's still able to put in 25 amps. When you have even lower, then it can withstand a much higher current. We also test the number of pulses, so 10 pulses per 10 pulses per 8 milliseconds. And lastly, we have a new pulse definition for the PBF series. This definition is a new setup where we try the pulse duration of 1 millisecond, and the condition is when the part is running at room temperature until a difference of 40 Kelvin. Usually we can see that at 1000 milliseconds, so 1 second, most PBFs here can take at least 40 amps in current. So yes, thank you for listening to the presentation. Any questions are welcomed.
So thanks from my side, Jan, for this great webinar. Like my colleague said already, we would like now to turn our attention to your questions, and we will just wait a little until some questions have come in. In the meantime, I would also like to draw your attention once again to the fact that in a few days you will be able to watch the webinar once again on our website or on our Würth Elektronik YouTube channel. And after the webinar, you will also get a separate email with all the information and the link to the recording of today's webinar. So now let's check the questions. So the first question that we have this afternoon is, when do you use a ferrite and when do you use an inductor to filter noise?
As the functionality of a ferrite is to remove noise, and for an inductor is to store, there's your first big difference. An inductor, you want to store, you want to store energy, and for ferrite, you want to dissipate the energy, aka filter. And so, as I've mentioned, there's a region where you want the impedance to be as high as possible, so more towards the resistive region.
So we're going over to the next question. There's someone having a question about the slide with the Curie temperature. Is the effect completely reversible?
Okay, so for the Curie temperature, when, for example, if you're soldering a PCB ferrite onto your PCB and you pass it through a reflow oven, this will definitely go above the Curie temperature. For example, reflow at 260 degrees. When that happens, the ferrite resets. You can think of it like a reset. It'll reset itself, where technically the magnetic dipole inside aligns and it becomes the highest possible like impedance. So when you measure this ferrite, a freshly one out of the reflow oven, and to one used in application, you'll see a bit of a drop. That's because when you put some current through, the ferrite will then adjust itself and decrease. So yes, it's reversible as long as you don't use your ferrite in application above the Curie temperature, then it won't reset again.
The next question that we have, if a ferrite is an inductance, why don't you mention the impedance in Henry in your data sheets?
So, again, the ferrite is used as to filter noise. Storing the energy is not important. So here we don't really consider the inductance. So we don't consider writing the inductive value, as usually the ferrite inductance is more unstable. It will saturate a little bit more than your standard inductor. Yeah, I think.
Okay. And as I see right now, we're only having one last question. Does the old ferrite with the new setup are going to be measured again? And do you update the old data sheets?
We do have a plan next year to measure all the ferrites, all chip bead multi-layer ferrites, so that we can update the data sheet to the new measurement setup for up to 8 gigahertz. So to show you more frequency, how it behaves in the higher frequency, and for DC bias up until its max rated current. So yeah, this would be the next step next year where we update our sheets.
Okay, I've now just checked all the questions. We are not having any questions anymore right now. So I hope this means that every question has been answered already within the webinar itself. So in this case, I would just like to thank everyone for the participation today. And as this is our last webinar this year, the next one is going to be in February 2020. We would like to thank everyone for participating in our webinars and wish you a good last part of the year and hope to see you in 2020 again. Thanks again, Jan, to you, and have a nice afternoon. Bye-bye.